Okay, so I'm gonna tell you one thing that you don't know here, but mostly we're gonna rely on things that we already know, and we're gonna apply it to get a really cool reaction called allylic bromination. Now recall that it's the weakest CH bond that's going to be substituted with the halogen, right? Because it's going to get hydrogen abstraction faster than the others, and the weakest, that is in terms of the lowest bond dissociation energy, that's going to be the one, right? So alkenes selectively undergo hydrogen abstraction at the allylic carbon. Why? Well, remember, now here's the vinylic position, here's the allylic position, and here's the nothing position. So recall that the nothing position for secondary is about 402 kilojoules per mole. Allylic is a lot less. Look at that. That is a very much of a weaker bond. And this is more. And we got that on in a previous conversation. You learned that vinylics were high. So why is this so much lower? Well, it's so much low. Actually, we learned this in a previous conversation also. Why is it so much lower? Well, it's lower because it is resonance stabilized, right? So once we abstract the hydrogen, so here comes the hydrogen gets ripped off, right? This is not a proton transfer because it's taken an atom, not a charged particle. Once this goes off like that, and this electron goes there, then you have a radical left, right? Well, it's resonance stabilized, right? We saw that before. So this electron can go here, then one of these pi electrons can come over here, and then we form a new pi bond here, and sure enough, we have the radical there, right? So you've seen this before. Hopefully hopefully that's starting to look familiar. Now, since that's the case, it's much more stable. So bromination of an alkene then is selective for the allylic carbon. And remember now, the benzylic is even more so, right? Where was it here? CH3, I'll put CH2. That one's even lower, right? Because that one we would be able to resonate. If that became a radical, we could share that around the whole ring, like I showed you in a previous conversation, right? Okay, now here's the problem with this. If we add bromine to this, then bromine competes with addition, right? So you're going to get, we saw this in a previous conversation, we're going to get some of that also, right? So, and here's the thing that I haven't never told you before, I'm telling you now for the first time, we're going to use something called N-bromosuccinimide, okay? You don't need to remember the structure of this. I don't think it's going to help you to know it. NBS is what it is. You know, it may be helpful for you to memorize that structure just to get used to stuff, right? But this, it turns out, has got a very weak bond, a very, very weak bond. So it doesn't take much energy at all, just a little bit of light energy here to produce a bromine radical, right? So we never had the Br2 in solution. So we use NBS, and it keeps bromine radicals around, and it keeps a little bit of HBr and a little bit of bromine in the solution, but it keeps it minimized. Okay. All right. So propagation then produces the allylic radical, NHBr. HBr reacts with NBS to form Br2, and this goes all over again. It starts all over again. All right. So where are we here? And so and that's it. Okay. Now you have to appreciate though, with asymmetric alkenes, we're going to get a mixture, right? So here's an asymmetric alkene, right? Because when we go through the intermediate, right, the radical goes here because we've got a hydrogen here, right? That's the allylic hydrogen. But once it comes off and it's resonance stabilized, then we get some of that over there too. So the challenge for us now is that we're going to get some bromine here in the termination step and some bromine here, right? So it's not necessarily a good thing. Okay, so if we're trying to make things, then symmetric alkenes are going to give us by far a better use with this.